Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GHEtool Cloud. And today we're going to do something else. So on this YouTube channel we already talked quite a lot about the physical background of borefields. We talked about the methods, the tutorials of GHEtool Cloud. We talked about the input parameters. But today we're going to do something else. Because if you really want to learn how to design a proper borefield, you need to exercise. And that's exactly what we will be doing in this new type of videos, let's say, is that I will go over projects I did myself or some user of ours did, in order for you to learn about how that project went, what were the design challenges, what can we learn from this particular design project, let's say. And the way we're going to do this is over in the article, which is linked in the description. All the input parameters are also listed, and a couple of questions that can help you design this borefield. Now in this video, I'm just going over it and learn and tell you what you can learn from these questions. But it's really helpful if you want to learn yourself, that you go over to the article, make it yourself, and then check with the reasoning in this video. So let's jump into it. So the project is a new, rather big office building in Ghent, which is a city in Belgium. And what we will learn in this exercise is to size a borefield for a building which has a high cooling demand, which is not the same as sizing for, let's say, a residential building. We will learn the influence of the thermal gradient on the design. We will talk and learn about the effect of sizing with monopropylene glycol versus sizing with pure water. And we will also talk about single and double U-tube systems. So let's talk a little bit more about the example case. Now this is really encyclopedial. So the input parameters, what we will do is we will work with minimum and a maximum fluid temperature of 2 and 17 degrees. The 17 degrees is to ensure passive cooling for this project. The minimum average fluid temperature of 2 degrees is to make sure that we're staying with positive temperatures, because as we discussed earlier, having a minimum average fluid temperature of 2 degrees means that we're coming out of the heat pump into the borefield at around 0 degrees, and we come out at 4 degrees. So if you have a delta T of 4 degrees across your borefield, the average is 2. We will start in January and simulate for 40 years. The ground parameters, I have here a table of the ground data. You can see it's loam and sand. Some loam sand, but an important layer which will play a role in this project is this clay layer, which, as you can see, has a really bad thermal conductivity. Now we could work with this table in GHEtool itself. For the time's sake, we're not going to do that in this video. We're going to work with some averaged out homogeneous thermal conductivities, which we calculated based on a table above on the previous slide of 1.6 at 150 meters and 1.7 at 100 meters, since we're less in the clay region. The volumetric heat capacity is 2.4 megajoules and the location is Ghent. Now for the borefields, just to keep it simple, we will stick to rectangular designs. We will stick to a spacing and length and width direction of 6 meters, a buried depth of 1 meter, and our original design, which we will start with, is 15 by 13 boreholes of 150 meters borehole depth. For the borehole resistance, we will work with a double DN32 PN16 pipe. We will use a borehole diameter of 140 millimeters. We will use a spacing of 40 millimeters and a rather good grout of 1.5 watts per meter Kelvin. And for the fluids, we will start with 30% volume percent of monopropylene glycol and a flow rate of 0.2 liters per second. And lastly, the loads, we will use the following heating and cooling loads. 300 kilowatts for heating with almost 400 megawatt hours per year in energy demand, and a COP of 4.5, and in cooling we have a higher peak load of 336 kilowatts, but lower energy demand on a yearly basis, 269 megawatt hours. And we have an SEER of 20. So with these values, you can enter it in GHEtool yourself, play around a little bit, use the questions in the article below. I see you in GHEtool. So here we are in GHEtool. I've entered all the information we discussed before. So let's jump to the results tab. And as you can see, we have a rather balanced bore field in this case, with a maximum average temperature slightly above the 17 degrees threshold. And this is the first thing I wanted to discuss with you. Strictly speaking, you can say, well, it's above the threshold, so we need to increase our bore field because we said 17 degrees Celsius is the maximum temperature. Now, we always need to take into account that we're working with assumptions. In this case, we're working with a monthly load resolution, which is not that accurate, let's say. We're also working with a very high cooling peak, 336 kilowatts. Now, given the uncertainty in my project that was on this peak load, let's say, we can say that 17.17 degrees C is actually good enough for us. Now, of course, if you're really sure about your energy and your cooling demand, perhaps you can say for your project, well, this is not acceptable. But in our case, it was. I also want to draw the attention to the Sankey diagram rather quickly. If you have not watched our video on the Sankey diagram, please do so. It's linked in the description. But as you can see, the ground source heat pump gets most of its energy from the seasonal thermal energy storage, basically the cooling. And it's only a very small portion that's actually in balance. So this project was really how you want to use a bore field. A really small imbalance and quite a lot of energy that's stored over the seasons. And you can also see that the ground does not cool down that much. So this was our initial design. We need, as you can see, 29,000 meters of borehole length. Now, if you recall the ground layers, we're now at 150 meters deep, working in the clay region. So let's go ahead and create another scenario where we say, well, let's go a little bit out of this clay region, go to 100 meters deep, and let's increase the number of boreholes in order to compensate for this. Now, if we do so, you'll see that we end up with a temperature profile perfectly below our 17 degrees, but with a borehole length short of 22,000 meters. Now, this is a second thing I wanted to show you, is people are really used to working with rules of three. So we said, okay, we started with 29,000 borehole, total borehole length. We go to boreholes of 100 meters deep. So we need to make sure that we drill so many extra boreholes so that we have the same total borehole length. But this is not the case. And it's not the case due to the fact that different boreholes configurations have different G functions and long-term effects. That's one thing. But also the ground temperature changes. We have here an average ground temperature of 12 degrees C, where before we had one of 13.27 degrees. And since this bore field is limited by the cooling demand, having this lower ground temperature actually means that you don't need that many boreholes to cope with it. So for this project, as for basically every project in geothermal engineering, you need to calculate certain things. You cannot just work with a rule of three to calculate the new design. So this is what we did, but we actually made a small mistake. Perhaps you've noticed. I said we went from 150 meters to 100 meters deep, but that also means that our average ground conductivity changes. And let's go ahead and take that into account. And this also stresses the importance of using ground layers, because when we're now not that deep in the clay layer, we actually have a better conducting soil. Now let's see if that has an effect on our design as well. And as you can see, it has, because now we're at 16.66 degrees C instead of 16.9. Now why is that? A couple of reasons. First of all, the ground conducts the heat better, so it can dissipate the heat slightly better, but also the average ground temperature changes. Now perhaps you can find this strange at first sight, but you have to recall what we discussed in an earlier video, that the way the ground temperature is calculated is using the geothermal heat flux from the earth. So the earth is warm, it dissipates heat through the crust, but since it's a flux in watt per square meter, depending on the conductivity of your soil, if it's a good or a bad conducting soil, it changes the gradients. So since we're now working with a slightly better ground, the gradient is a little bit less steep, and also our ground temperature is a little bit lower than we had in scenario 2. So a slightly lower temperature also means a slightly lower fluid temperature. And this also means, let's create a fourth scenario for that one, that we can perhaps decrease the number of boreholes again. Let's see where that brings us. So yeah, we're still under the 17, and now we're at 21,000 meters borehole length instead of the 22. So okay, what we now did is we basically drilled less deep, we increased the borefield size, and we saved quite a lot of borehole meters. So up to the next question. What we said is we're now working with 30% of monopropylene glycol, which is typical in Belgium, which gives us a freeze protection of -14. Now in this case, we only go to 7.7 degrees Celsius. So we actually don't need antifreeze. So let's go ahead and simulate this bore field with water. So we go to the resistance tab, we say, well, work with 0% antifreeze. And if we're working with antifreeze, we also need to change the minimum temperature. Now this depends a little bit on your heat pump manufacturer, and please check the technical data. But what we typically see is that the outlet of the heat pump should be above 4 degrees. So if you work with delta T of 3 to 5, let's say, you need at least 5.5 degrees on average. So if we say here it's 5.5, this means that we're injecting 4 and we're extracting 7 from the ground. So that's an average of 5.5. But please check with your heat pump manufacturer. Let's go ahead and simulate this project and see where we end up with. One important thing to notice is that our effective borehole thermal resistance has changed dramatically from a laminar case to a transient case in extraction and even turbulent in injection. And also our fluid temperature has dropped due to that. So what we can do is, since we're now working with water, is that we say, well, let's decrease the number of boreholes again. Let's go to 15 perhaps. Let's see where that brings us. So we're working with water, the heat transfer is better. And so we can, perhaps even more. We're at 16.5. Let's go to 14 perhaps. So we can again reduce the bore field size due to that. Now we're at 16.9. Perhaps let's keep it that way. It gives us 18,000 meters borehole length. And as you can see, we're still quite a lot above this minimum threshold. So that's an important thing. In this case, since the temperatures were high enough, we can work with water, and that's beneficial for a system, for a borehole thermal resistance. And for the pressure drop, as you can see, it's also better, because monopropylene glycol is really viscous. It's almost honey, let's say. So working with water is also a good idea from the hydraulic side of things. Now, as a last variation, we now worked always with a double U-tube. Let's say how the story changes when we work with a single U-tube. So let's go ahead and calculate this situation again. So we use now a single DN32. And here we see that, yeah, first of all, the pressure drop increases, which you can imagine. We're now having a way higher Reynolds number. The borehole effective thermal resistance also increases. And this is relative to the one with the double U-tube, since here we're also already in the rather turbulent region. So if we go from a double U-tube, which is in turbulent region, to a single U-tube, which is turbulent, yeah, our fluids, our convective heat transfer is already really good, and we're just lowering the number of U-tubes. So that's not beneficial. Going from a double to a single U-tube can be beneficial, typically when your double U-tube is laminar and your single U-tube is turbulent. But if it's both turbulent, in this case, it's not beneficial. So we need to increase the number of boreholes again, I think to, let's say 15 by 13 boreholes to end up with a system, yeah, let's say it's 17 degrees C. So we need to drill, what is it, 13 extra boreholes in order to compensate for this single U-tube. So in this case, it's not a beneficial. And this was basically what we wanted to show you in this exercise, that depending on the depth you pick, the fluid you choose, you can have either a bore field of 29,000 meters or 18. So that's a really significant difference. So bore field design matters, but of course you're here, you already know that. I hope you found this case interesting. I hope you learned something whilst playing around yourself. If you have projects from your own that you think would be interesting for this series, please let us know. If you have questions, also let us know, and I'm looking forward to seeing you in the next video. Take care. Bye.